So let's welcome our next speaker, who is Harry Saxton from the Sheffield University. He will tell us about the personalisation of cardiovascular models using Julia. So go ahead.
Yeah, thank you. So I think this talk is slightly more high level about we're just starting a new project. We're interested in this, as is everybody in the NAN, this application of digital twins and personalisation. And it's more about the application of the methods rather than there is obviously a physiological focus here, but it's just kind of saying, okay, if you're looking to develop this pipeline, how Julia's kind of already there and ready for us to start implementing these things. So our focus is on pulmonary hypertension and on trying to simulate global dynamics. So we focus on these lump parameter models, which just give simplified representations of the cardiac system. So we've got 4 chambers, ventricle and atria, with systemic and pulmonary circulation. And hypertension would typically indicate an increased resistance around the vascular bed or the arteries. So the aim is saying, okay, can we develop these models that they can get even larger in size like this, or even one for the venous system, and they can eventually get really silly in terms of size. So it's about saying, okay, how do you strike that balance between ensuring you obtain these key biomarkers that indicate pathophysiology, but also a good enough representation of the anatomy. So you can combine representations of the legs, like we've got here, with 4 chambers and see what happens. So what do these model components mean? The resistances are viscous dissipation, so you've got arterial blockage, indication of a resistance, i.e. some pathophysiology there. Inertia, represented by an inductance, and then vessel distensibility, so how much does an artery contract and release. So quite intuitive representations of each compartment. So what do we mean, I think, first by personalised medicine? It's about this, I think, it's about the combination of both model and data. You've got to say, okay, is the model parameterized by these biomarkers? Are the values realistic? And the model gives you something back. And what does it give you? It gives you these indicators of pathophysiology. So venous compliance, systemic resistance, pulmonary resistance, but then also the data. It's what can you obtain clinically? What describes that patient's physiological state? And the combination of both of these eventually produces this personalised medicine. But if we start to carry on and develop these really complex models, they might go from subcellular level to organ level. What can you do offline? So without this straight jump to patient data and say, okay, well, how quickly can I just ram as much data into my model as possible? What can you do in terms of, I think this is the real big one and the real stopper for clinicians in my experience, is about this risk prediction. What's this uncertainty associated with any predictions that you're going to make? What's the uncertainty associated with you saying, okay, this is a biomarker of a specific pathophysiological state? So this is the best attempt we've got so far and our finest PowerPoint work at trying to develop this workflow of saying, okay, what can be done offline? What can be done before you end up actually showing it any data at all, to provide this quantification of the uncertainty, along with obtaining a subset of parameters that are constrained by what's going to be available to you. So quite often you'll see people perform in sensitivity analysis and subset reduction with just a choice of outputs that tickle their fancy. However, when it comes to actual calibration of the model with the experimental data, there's a mismatch between that, because what may be available in clinic is not what people have done the subset reduction on as well. So it's about saying, okay, can we combine both the experimental stage and this preparation to create a complete whole model? So, I'm going to try and go through. I'm going to try and go through the majority of this and just highlight, okay, what packages are available and how they've helped us in the production of trying to generate these personalized models. So, model construction, first of all. What is available? It is a shameless plug. I am involved in this, but we've had nice uptake in the hospitals, especially from clinicians. So, a 4-element Windkessel model can be generated through these two differential equations. If you were to combine the 4-chamber model and the venous system, you'd be here a very long time in trying to write down some equations. So that's how it might look in MATLAB, where you write your differential equations and solve them. But what's the jump that we made in into modeling toolkit? It's been able to define the old been able to define individual compartments just through individual segments, and then combining them based on whichever direction the flow may be going. So it takes its inspiration from Simulink and A-causal modeling as modeling toolkit in just providing clinicians with this, okay, drag and drop representation. Because we've now got cardiologists who are almost see it as a little game in saying, okay, can we reproduce bits of the cardiac system? Can they put together some sort of circuit that gives them values that they've observed in clinic? And writing out the differential equations was absolutely a no-go. But when all they have to change is which compartment and the direction what it's connected to, it makes it a lot easier for them to get on board. What does it have available to you? Built on top of modeling toolkit. You can link to SPML, CellML. There's a whole range of nonlinear compliance, valve functions, and then 3 heart descriptions as well. And we're constantly trying to build upon this to get more and more, as ones pop up in the literature, try and get them imported in. Global sensitivity analysis. Why is this important? So this allows us to then obtain, okay, what's the risk associated with any predictions? So we're saying, okay, what are the impactful parameters that contribute to the outputs that we've got in our system? Allows also for what's the word I'm after? Confidence intervals, so you can do bootstrapping, resampling with replacement, that allows you to say, okay, how confident are you in your global sensitivity analysis results, which is something that is vital in this, being able to provide that. It all comes back to this quantification of risk. What's the risk associated with any predictions you're making? And then also gain physiological insight. So this is just another, it all really stems from the Sobol indices that you can obtain. And this is then the 4-chamber model, a more advanced one that I showed before, that's popular for benchmarking and things like this. And if we need to perform a sensitivity analysis, we need K, P plus 2. So P is the dimension of the input space. K is the number of samples that you've got. And I'm going to show some quite typically Julian showy-off kind of metrics about the differential equations, but there is a point to this. So if we wanted to do this in MATLAB, Python, CellML toolkit, what this is about is this reusability, so this standardization between the fields. So this, the model I showed before is on CellML, and then from them you can go, okay, click, download the code, run the code, get the outputs. And that's what the people who do the clinical work are interested in. And so what these are metrics for doing that exact thing. Of I go to CellML, I download the generated code, and I click run. And no way, no way in hell do I believe that if anybody wrote their own script, that would be the result. But the people we're trying to engage with are not software developers. These are clinical personnel. So you can see straight away, in terms of performing the sensitivity analysis, if you need to do millions of runs, we're way up on what's available out there for the reusable and standardized metrics so far. And this is just another quite example for why this is important. So the solid lines are sensitivity metrics, and along the bottom this would be increasing sample size. Investigations have been done about, okay, what are the sensitivity indices and their convergence. You see, the typical literature value for this sort of thing is where the red line would be, and people would take their sensitivity indices at that point. But for cardiac models associated with the nonlinearity, the stiffness and things like that, you've got to go a lot further on. So essentially this whole thing boils down to how quick can you solve the thing. And I'm not here to parrot the differential equations, but for from a clinical perspective, this allows us to do the quantification of risk better than what tools have been available so far. Subset selection. So if you're interested in a pulmonary hypertension, for example, and you've got a set of outputs, you do the sensitivity against a set of outputs. How do you reduce, if you've got 60 or 70 parameters and you've only got 3 measurements, well, good luck trying to obtain some sort of identifiable insight into that. So it's about saying, okay, how do you obtain this subset in that can be personalized to the clinical data that you obtain? So E represents, quite unintuitively, influence. D is the orthogonality, and I is this, what they call this identifiability index. And this is about saying, okay, can you rank the parameters and give me the best group of parameters that are not only influential, but they're also orthogonal. So the idea behind that is saying, if you've got a response surface for a set of outputs, you need to make sure that the influence of the parameters is orthogonal. So if I stand behind somebody and we both throw a ball in the same direction and somebody turns around, you've got no way of understanding who threw a ball the furthest. So you need to be able to differentiate between the parameter effects as well. So them just being influential doesn't always cut it. So there are functions on the Global Sensitivity Analysis GitHub page that do this. I just need to refactor them into the way that is deemed appropriate by the higher echelons. And then uncertainty analysis. I will die on the hill that there is a difference between uncertainty quantification and uncertainty analysis, because sensitivity analysis is a practice of inputs. So it only cares about the inputs. It tells you, okay, what inputs are influential on the outputs. You've got no clue that the bounds you prescribe to a sensitivity analysis give you physiological outputs. There's no way of, to date, as far as I'm aware, there's no way of knowing that that's true. So what uncertainty analysis does is says, okay, given some sort of bounds that you put on the parameters, what are the maximum and minimum outputs that you get? So for example, for us, if we end up with a maximum ventricular pressure of, I don't know, 10 mmHg, well, there's no point us even exploring that region of the space, because anybody who's got 10 mmHg is brown bread, dead. So that then gives us a great way to do this. So we can do this through measurements.jl, linear propagation of the errors. So this is really helpful for medical device errors, where we know that there's kind of a consistent level of error associated. So you can just propagate that error through. It makes things really helpful. Monte Carlo measurements, if you move across to a more statistical approach, you can do the distributions of numbers. So it makes it a lot easier when trying to explain to clinicians that about the adding and subtracting of distributions and things like that. And then probnum diffie q allows us to solve these and compute posterior distributions as differential equations. Kalman filtration, so this is all about saying, okay, once you've obtained this subset of parameters, and you know that you need to then begin to calibrate this against some patient data, how do you go about that? So there are a host of control packages for data assimilation that exist out there, and I think they've all got the benefits of, they've all got drawbacks and benefits. So I think the best one that we've found for this application so far is about the low-level particle filters. So these, the valve functions are quite, and the resistors obviously are algebraic equations in our models. So being able to represent and do a data assimilation problem for differential algebraic equations, that's always a really big help. But then also, I've recently come across a new method for data assimilation, which is about implementing it as a callback. So quite often when you're performing the data assimilation, there's discretization to a either an Euler scheme, or if you're lucky, a Runge-Kutta fork, because nobody's going to be writing n order steps. But what the callbacks allow you to do is to leverage the higher order solvers, so the Verne 7, the Verne 9s, but implement it at each time step. So you get the higher order accuracy of the ODE solver, which normally would be lost in data assimilation problems. Yeah, so, and this is where I think Kalman filtration for the personalisation just is a really intuitive thing. It's just about the combination of, okay, what is the prediction, what is the experimental data you've got, and give me your best estimate for this personalised subset of parameters. Profile likelihood, and big shout out to the workshop yesterday, which I'll try and beat him into putting into a package about profile likelihood. So far we'd come across profile likelihood and likelihood profiler. These do all have drawbacks, which I don't think yours does, so please put it into a package, please. And that gives us then some insight into the identifiability of associated with the parameters that you've obtained. Subtlety involved in this. The profile likelihood and optimization tell you slightly different things. So what we've done here is we've done an identifiability analysis, but in a theoretical sense. It's saying, okay, in the best case scenario, what are the subset of parameters that you're going to obtain that will give you insight into the information about that patient? And then when we eventually do show it clinical data, when we do show it the clinical data, the optimization is just giving us some sort of parameters. We've got no clue as to whether they are identifiable, whether they are unique. And this is where the profile likelihood comes into play. Because then we can see, okay, theoretically we've obtained the best subset of parameters. However, practically, when you've got the noise of the data, you've got the measurement error from the machines, is that subset of parameters still identifiable? And any issues with any identifiability then can be attributed to measurement error, noise error, things like this. Yes, before the big sell. So that's that. And this is obviously an iterative thing. This is not a one-time job. I think the majority of the creation of the model is good, and that should be reused, but it's important to acknowledge that you're consistently constrained by the experimental data that you've got available. And every time there is a new data, this is a new dimension, you need to go back and do this whole process again. So this is then the big sell, this CVD net. So I'm starting a postdoc with Imperial, Sheffield and Nottingham, so I've been rolled out to do the cell. And it's all about the personalisation of pulmonary hypertension patients. So we're looking at saying, okay, over a 5-year period, can you observe deterioration? And we've got an abundance of kind of horribly invasive data and things like that. So if anybody does know anybody that's interested in a job, please do come and speak to me. Yes, thank you very much. So that is then a QR code, I think, for any of the literature that backs up some of the subset selection and things like that. But I'm more than happy to converse over anything. Okay, thank you very much.
Thank you for your talk. Are there any questions here?
It's lunchtime.
Yes, thank you very much for your talk. It was very interesting. I was wondering, I imagine it could be possible that you would find multiple subsets of parameters that would provide you with a similar, or at least would be good. How do you choose between the subsets?
So that is true, but this is supposed to alleviate that essence of choice. There is, because it's trying to remove that. Okay, I'll choose this, I'll do this, as much as possible. With this algorithm, the only one choice that you have to make or put is that the parameter which comes out as the most influential across all the outputs, that goes in first as the identifiable starter of the parameter. And then from that point, it's a recursive algorithm that you make no choice in. That you say, okay, compute the orthogonality of that against all the other ones, multiply it by the influence, whichever's got the highest identifiability index, that then goes in. And then do that against them two sets, against the other ones. So it's computed through a linear span, so you compute. It's the linear orthogonality between the chosen ones and the ones that remain in the set. So it alleviates that essence of, okay, do I have to, which ones do I choose? What level of cutoff do I put? Because this is all, there are obviously definitions for these, but they're all normalized between 0 and 1. So you can essentially, the set that you end up with, as soon as it starts to get towards like 0.05, well, that's a 5% chance of that being identifiable theoretically. Whereas the ones up the top are 99, that kind of business. So the answer to your question is this method alleviates that choice of subsets. There are other methods out there, which one is called a structural correlations method. So that's by a group in America, and that is more clinical choice. So saying, okay, you obtain multiple subsets, pick the one that looks clinically the best, kind of thing. So it's swings and roundabouts.
Thank you.
If there's no further questions, then thank you. And thanks to the speaker again. I hope you enjoyed this session, and afterwards there will be lunch. So enjoy that too. Thank you.